Okay, so it looks like it started. Hello everyone, welcome to the MATH2501 2601 seminar. My name is Jerry and I'm going to be doing the first two topics today. Okay, so it looks like it started. Wait 1 second. Yeah, so I'm going to be doing the first two topics, group theory and vector spaces. And Steve is going to do topics 3 and 4. And also keep in mind that the first topic that I'm going to cover is Math2601 only. So yeah, if you're doing Math2501, you can take a nap for 20 minutes. Cool. So we start with groups. So a group is a non-empty set with an operation defined on it, and it has to satisfy 4 conditions for it to be defined as a group. So it has to be closed, which means that if you have 2 elements of G and you apply the operation between them, the result has to also be in G. Associativity, so you can kind of just move the brackets around. Yeah. Existence of an identity. So there exists an identity element such that if you do an element and you do the operation with the identity element, you get back the element. And an existence of an inverse. So for any element in the group, there exists an inverse element where if you do the operation between these two, you get the identity element. And furthermore, if we have this property where A star B equals B star A, where star is the operation, we can say that the group is an abelian group. So we start off with an example. So it says let G be a set of matrices, non-zero matrices. Prove that G is a group under matrix multiplication. So we're going to solve this question by using these definitions, these conditions that we just stated. So we have to prove that all of these are true. Therefore, G will be a group. I'll just preface this by saying there's a shorter way where we'll cover just in a moment the subgroup lemma. So we can technically consider that G, we'll find that all the elements, all the matrices in G are invertible. So we can technically say that G is a subset of all invertible 2x2 matrices. So then we only need to do the subgroup lemma, which I'll talk about. And proving that G is a subgroup using the subgroup lemma is quite a bit shorter. But for now, I'll just prove that G is a group using these 4 definitions of a group. So first, we actually calculate the determinant of any matrix in G. And obviously just is the product of these two minus the product of these two. And we find that it's always positive. And this is never going to be 0 because we know that G is a set of all non-zero matrices. So that means that all the matrices in G are going to be invertible. And when we prove closure, we have to keep in mind that G is the set of non-zero matrices. So while we have to do the usual stuff to show that what we get is in G, we have the additional thing to prove that what we get in G is not going to be 0. So first we start with the closure property. So if we assume that P and Q are elements of G, so they're matrices. So we just let P and Q look like this. So we have A and B for P and C and D for Q. So now we have to prove that PQ, since the operation is matrix multiplication, we have to prove that PQ is also going to be in G. So first we start off with PQ. So that's just our matrix multiplication. and we end up with this as PQ. So obviously, just for the first entry, that's going to be AC minus 3BD. And to prove that PQ is kind of in G, we need to show that it follows this structure. We need to show that the entries of PQ follow this structure. So therefore, we kind of consider this to be the X, and we consider this to be Y. And then next, we kind of have to do some algebra to prove that this is going to look like minus 3y. So you have to prove that it's minus 3 lots of here, y. And this kind of looks like x plus 2y. So if you kind of shift around with the brackets to show that exists, that's how we prove that PQ is going to be in G. So that's what we do. So as you can see here, these are all equivalent. We just kind of shift it around. So we have here x, y, x plus 2y, and minus 3y. Yep, so that means PQ is closed under matrix multiplication. And also, the product PQ can't be 0, because remember, G is a set of non-zero matrices of that form. It can't be 0 because the product of two invertible matrices is also invertible. So that's all we need to do for closure. For associativity, it's pretty short. All we need to do is state that matrix multiplication is known to be associative. So if you have two matrices here, we can shift the brackets around. And for the identity element, well, we can kind of just outright state for matrix multiplication. We know that if you times a 2 by 2 matrix by the identity matrix, 2 by 2 identity matrix, we're going to get the same matrix back. And we know that we can make this when we set x to be 1 and y equals to be 0. Yeah, so if we set here x to be 0, x to be 1, and y to be 0, we get a 2 by 2 identity matrix. So we know that the identity matrix is in G. And also we know that the set is now non-empty because we at least have one element that we know for sure is in the set. We have to remember that under the definition of a group, we have to prove that the group is non-empty. So make sure to state this. And we need to show that the inverse is also in G. So since we have an element x, a matrix x in G, we need to show that the inverse is also in G. So we just start off by calculating what the actual inverse is. So to calculate the inverse of a 2 by 2 matrix, we do 1 over the determinant. So we calculated this before. So this here is 1 over the determinant. And we flip these values and apply a negative to these values. And then like we did before with closure under matrix multiplication, we kind of create these equivalent statements to kind of show that this is kind of like the x and this is kind of like the y. So we need to show that the x inverse follows the structure of x and y in the matrix, in the group of G. So since X inverse is never going to be the zero matrix, every element does have an inverse. And yeah, so we've now proven all four properties of a group. So we've solved the question that it is a group under matrix multiplication. So furthermore, we just have some more properties of groups that we should just keep in the back of our minds when we solve questions. So if you apply the inverse twice, you're just going to get the same element back. And if you apply the inverse to A star B, you get B inverse A inverse, B inverse star A inverse. And here, if A star B equals A star C, then B and C are going to be equivalent. And the same thing for the other way around. So if B star A equals C star A, then B and C are going to be equal. So we kind of extend the definition of a group to a field. So here a field has two operations compared to a group which has one operation. And for both of the operations, the field is abelian. So we remember that abelian is A plus B equals B plus A. And over the scalar elements of the field, they're distributive. So yeah, we can distribute over the bracket. So with groups, if we have a non-empty subset of a group, we can say that A is going to be a subgroup if it satisfies these two properties. So it's closed under the operation. So for A, if A and B are in A, then A star B is also in A. And every element in A also has an inverse in A. So yeah, you don't have to prove all four properties, you just have to prove these two to show that a set is a subgroup under a certain operation. So we start with an example. So let G be a group. For any element of G, we define the set CG to be where if X is an element of G, then Gx is going to equal to Xg. And then we have to prove that Cg is a subgroup of G. So we pretty much have to prove three things that come directly from this theorem. So we have to prove that Cg is non-empty. Cg is closed under operation. So if we have two elements of Cg, since the operation is multiplication here, xy has to be in Cg as well, and the existence of an inverse. So if we have x in Cg, we have to show that x inverse is also in Cg. So we start off by showing that Cg is non-empty. And an easy way to show that a set is non-empty is to check for the identity element, because it's usually quite easy to check for an identity element inside a group. So we pick the identity element E from G, and it has to satisfy this rule. So Gx has to equal to Xg. So here, the X is E. So we have to show this is true. So we start off the left-hand side as GE. And since E is the identity element, GE is just going to be equal to G. But we also know that G is equal to G times the identity element, GE. So we've shown that since GE equals to EG, this rule is satisfied, so E is in CG and G is non-empty. So first, then we check closure. So consider that we have two elements of CG, and since we have these two elements of CG, we know that this is true. Because yeah, if they're in CG, they have to satisfy this rule. So to prove closure, we want to show that xy is going to be in CG. So we pretty much have to prove this statement here. And the way we're going to do that is we're just going to start off with the left-hand side and use these two pieces of information to try to get to the right-hand side. And then, therefore, we can show that this is true. So we start off here with G bracket xy. And here we can shift the brackets here because of associativity of multiplication. And using this piece of information, we can switch out the gx with an xg. And then we just shift the brackets again because of associativity of multiplication. And we switch the yg with a gy. Or the other way around, yeah. We switch the gy with a yg. And we shift the brackets again. And we've shown what we wanted to show, which is gxy equals to xyg. So we have proven that xy is in CG, and CG is closed under operation. Next, we want to show that the inverse exists. So say we already have an element in CG x, and to prove that the inverse exists, this is the result we want to show. We want to show that x inverse is in CG. And if x inverse is going to be in CG, then it has to follow the rule. So this statement must be true. So in order to prove this, again, we're going to start with this. Actually, yeah. To prove this is true, we're going to start with this piece of information and multiply and alter this equation to try to get this equation. And if we kind of just observe what we're looking at, we're trying to get from x to x inverse. So that means we have to do two things. We have to introduce x inverse to the equation, as well as get rid of the x's. So to get rid of the x's, you're going to multiply by x inverse to get the identity. But also because you want the x inverse in the equation, we're going to have to add x inverse twice. So what we actually do is we add x inverse to both sides of this equation, gx equals to xg, because once we add x inverse to both sides, one side is going to neutralize the x that we don't want, and one side is going to have the x inverse that we want. And a similar thing happens on the other side. But just going through the left-hand side first. We can shift the brackets here because of associativity. And x inverse is going to become the identity element. So it's going to be x inverse g. And on the right-hand side, a similar thing. So here, this is going to turn into the identity element. And so we have x inverse g equal to g x inverse. And that's what we wanted to show. So we show that x inverse follows the rule in CG. So yeah, we've proved the three things we needed to prove. That CG is a subgroup under the subgroup lemma. So yeah, so this question is finished. So morphisms. So just like how we can define a mapping between any two sets, like from the interval of 0, 0 and 1 to R, we can define a similar kind of mapping between two groups. So if we consider two groups, G and H, the mapping from G to H is defined as a homomorphism if it satisfies this following formula, where this is the operation of G, this is the operation of H. Furthermore, if this mapping is a bijection, this means it's 1 to 1 and on to, we call and say that both groups are isomorphic to each other. And furthermore, properties of homomorphisms. So from this formula, actually, we can derive these two properties, that FA inverse is equal to FA, I mean, it's kind of strange to say, but yeah, if you just look at it, the homomorphism maps the inverse to the inverse. And also the homomorphism is going to map the identity element in G to the identity element in H. So we have an example. Suppose that G is equal to this matrix, set of matrices that look like this, is a group under matrix multiplication. Is the group G under matrix multiplication isomorphic to R plus? So to prove that these two groups are isomorphic, we need to first prove that there's a homomorphism from those two groups. And then afterwards, we have to prove that the mapping is a bijection to show that the groups are isomorphic to each other. So there's two things and two stages to this question. But then before we kind of go on with it, we kind of have to construct the mapping to each other, because this question doesn't really give us the mapping. And you have to kind of think, are we going to go from G to R or R to G? Because if they're isomorphic, it doesn't really matter, but it's definitely going to be easier for us to calculate if we pick a smarter mapping. So it makes more sense to go from R to G, because if we look at G, it's a matrix constructed from a real number. So we can kind of set the mapping to be f of t equals to this matrix, where we map a real number to a matrix. Since only a real number is needed to form this matrix. So yeah, so we selected the mapping to go from R to G, where ft gives us this matrix. And first we need to show that it's a homomorphism. So from the definition of a homomorphism, if we recall, but here the operations are plus and times, so we need to show that, or here we use s and t, so we show that s plus t equals to fs times f of t. So if we can prove this statement is true, then we know that this map is a homomorphism. So if we consider what the map is, it's kind of easier to show that the product of two such matrices forms this S plus T matrix, rather than kind of just starting from this S plus T matrix and splitting it up into two product of matrices. So what we're going to do is show that the product equals to the sum here. Because we have to prove this equation, but it doesn't really matter which way we go. So if we have fs times ft, we do some matrix multiplication, and we end up with this matrix. And we can see that this follows fst, or f of s plus t. So yeah, so we've proved that G is homomorphic to R. So now we have to prove that it's isomorphic. And here we keep it quite simple. We just say that we know that F is a bijection because it's injective and surjective. So if you just think about it, it's going to be 1-to-1 because here we have just S. So each S here is going to be mapped by only one real value. And it's going to be surjective because G is the set of all matrices that look like this from real numbers, and we come from all the real numbers. So we're going to be able to make any matrix in G that we want. So since the F is a bijection, the groups are isomorphic to each other. Yes, so this question is finished. So now for a homomorphism, we define two special types of sets that come from this mapping called the kernel and the image. So the kernel is a set of elements in G such that if you apply the map, you get the identity element in H. So if you kind of have G and H, and you have this subset of G, which is the kernel, they kind of map to just the identity element here. And the image of F is the projections of F. So the image is in H. So from mapping all possible values of G, that's the total set of what is mapped to in H. So a question. So let G be an identity, be a group with an identity element E. Let H be a group with identity element F, and let phi be a homomorphism. Show that if G is an element in the group G, and K is in the kernel of the isomorphism, then this thing over here is in the kernel of phi. So yeah, so if we just use the definition of what the kernel of phi is, we have to show that phi of this thing is the identity element, because that's the definition of the kernel. So to prove this is true, we're going to start off with the left-hand side, and we're just going to keep breaking it up using the formula of the homomorphism that we are aware of. So once again, if it's a homomorphism, this is true. So we're just going to use this formula to keep breaking this up and simplifying what we get to hopefully get F. So we have an element of G and an element of the kernel. Yeah, so we start here, the left-hand side, and we can break this up into two chunks over the second group's operation. And then we can break this up into two chunks again. But then what we realize is that since K is in the kernel of phi, phi K is just going to be equal to the identity element in H, which is F. And then obviously this is just going to disappear, which leaves us with phi g and phi g inverse. And since we remember that the inverse maps to the inverse for homomorphism, we can do this, where these two are equivalent. And since we now have an element of H and its inverse, that's going to be equal to the identity element in H. So that's all we need to show. Okay, so now I move on to the second topic, vector spaces. So if you're a 2501 student, you can come back in. So for vector spaces, vector spaces is kind of like a set of objects called vectors, and it has to follow these rules. But I'll just kind of skip over vector spaces and move on to subspaces, because that's kind of more relevant to what we're trying to do. So we have the subspace theorem. So suppose U is a non-empty subset of a vector space, then UF is a subspace of V if the following condition is met. So for X and Y in U, if this is also in U, then that's how we know that U is a subspace of V. And this formula here is just kind of it kind of joins two steps. So usually to prove that U is a subspace, we need to prove that there's closure under scalar multiplication. So lambda x has to be in U, and closure under vector addition. So x plus y is in U. But we just do it in one step if we just show that this combination is also in U. So we have an example. So let X be any non-empty set and Y be a subset of X. Prove that the set U, where so f is going to be a function, since here this is a function space of X. So this is just kind of like a set of functions. So we're going to be looking at functions where f of y is going to be equal to 0. And we have to show that U is a subspace of fx, the function space of x. Okay, so to prove this, we're going to use the subspace theorem. So we're going to pick two elements x and y of U and prove that lambda x plus y is also in U. And also, yeah, I forgot to highlight that it's important to point out when you're working out that U is non-empty. So same thing with groups. You have to prove or just show that it's a non-empty subset. Usually we can do this by just pointing out the identity element exists. So first, yeah, we're going to prove that it's non-empty. Since fx is a vector space, it contains the 0 function. So the 0 function is just the function which maps all of x to 0. And since y is a subset of x, it's also going to map all the y to 0. So if we have like a group of x that gets mapped to 0, since y is contained in that x, all the y are also going to be mapping to 0. So we know that the 0 function exists, so U is non-empty. Okay, so we start off with two elements of U. So if they're elements of U, we know this has to be true, because they're going to be mapping to 0 for all y. And then for a scalar element of the field, we want to show that this belongs to the space. And it's going to belong to the space if it's going to map to 0. So since this is a function, we can split it up and we can take out the scalar, and we know that fy and gy equals to 0, so we use that information to set this to be 0 plus 0, which is equal to 0. So this means that alpha f plus g is going to be in U, and we've fulfilled all the steps we need to prove in the subspace lemma. So we've proven that U is a subspace of fx. So now I move on to span. So suppose we have a set of vectors from v1 to vn. We define the span of W as the set of all possible linear combinations of the elements of W. And if the spanning set, so if S spans the whole space, we call S the spanning set. So just a quick example. In R2, if we just have these two vectors, v1, v2, these vectors span all of R2 because for any point you want, so say I want this point, we can have a linear combination of v1 and v2 that gives us this point. So if we just extend this by scalar, and v1 by scalar, we can reach any point in R2. We call a set linearly independent if the only linear combination of the set that equals to 0 means that all the scalars here are going to equal to 0. And if this isn't true, we say that the set is linearly dependent. And I'll approach it from the linearly dependent angle first. So, for example, say a set is not linearly independent. So if this statement is true, all these scalar values aren't necessarily equal to 0. So say we have that v1 plus 2v2 equals to 0. This means that we can write v1 in terms of v2. So with linear dependence, this means that we can write vectors in the set in terms of other vectors. So the whole idea with linear independence is that with all these vectors v1, v2, and vn, we can't write v1 in terms of any other vectors. So we can't say v1 is like v3 plus v7. This is not possible if the set is linearly independent. So we move on to a question. So if we let B be a set of FO, F1 to F3, where Fkx is equal to this, by considering limits as x goes to infinity or otherwise, prove that B is a linearly independent set. So whenever we prove that a set is linearly independent, we have to first find a linear combination and set it to 0. And if we want to prove that this set is linearly independent, we have to show that all the scalar values here are going to be 0. So therefore we can't write like FO in terms of like F1 to F3. This is not possible. So first off, we're just going to convert the FO into the actual values here. So for example, F0 is going to be e to the power of minus 0, which is just 1. And F1 is e to the power of minus 2x. So yeah, so we just replace the FOs here with the actual values. And the question asked us to consider the limit as x goes to infinity So if we just look at what we have here, if we consider the limit as x goes to infinity, all these statements are going to evaporate into 0 because e to the power of minus 2x, as you approach infinity, that's going to go to 0, and all the other negative exponents of e are going to vanish into 0. So this is all 0, and this leaves us with alpha 0 is equal to 0. So this means that alpha 0 is 0. So now we don't have to consider alpha 0 because we already know it's 0. So we're left with alpha 1 e to the power of minus 2x and so on. And next, what we're going to do is we're going to multiply the equation by e to the power of 2x. And the reason why we do this is because as it stands right now, all of the alpha 1s and alpha 2s and alpha 3s are going to disappear as x goes to infinity. So we want to isolate the value of alpha 1. So if we multiply this equation by e to the power of minus 2x, we get this equation. So since alpha 1 is no longer going to disappear as x goes to infinity, we multiply the equation by e to the power of 2x. And then we reconsider the limit as x goes to infinity. So as x goes to infinity, these are going to disappear. So alpha 1 again is equal to 0. And then you might have picked up by now that we're just going to keep repeating this process, which is going to show us that alpha 2 and alpha 3 are also equal to 0. And since we've shown that for the linear combination, if they're equal to 0, then all the scalars are equal to 0. So that's all you need to show that the set B is linearly independent. So now we're interested in basis sets. So for basis sets, we want a set that spans the whole space, but we want it to be minimal, which means that we don't want more than we need to span the whole space. Because if we have already what we need to span everything, if we add another element to this set, you can already make that element from the elements you have in the basis. So these two things are going to be true. So the span of S has to be the whole space V, and S is going to be linearly independent because you want to have the minimum vectors, which means that if there are two linearly dependent vectors, you just get rid of the ones that are linearly dependent. And yeah, so just some standard bases that you might already know are the standard bases. So for example, in R3, E1 is going to be 1, 0, 0. And for matrices, M1, 1 might be 1, and the rest are all zeros. Now we're interested in dimensions. So if we consider a vector space V, which has a finite spanning basis S, so the size of the basis is going to be equal to the dimension of the space. And then these three statements are going to be equivalent, where if S is a basis of V, S is linearly independent, and the size of S is equal to n, the dimension of V. And what I mean when I say these statements are equivalent is that if this statement is true, then we know that these two are true. And if this statement is true, then we know that the other two statements are true. And the reason why this lemma is quite handy is that if you want to prove that S is a basis of V, you can start off from one of these two statements and say that we already know the size of the set. So say you're given a set that has size 3, and that's equal to the dimension of V. So all you need to prove is that S is linearly independent. So the set that you have is linearly independent. And that's all you need to prove that S is a basis. So yeah, so this lemma is quite handy to keep in mind to save some time when proving a certain set is a basis. And we're going to apply this straight away. So consider a degree 2 polynomial vector space. Show that the following set is a basis of the vector space. So we're given 3 polynomials here, which are supposed to span P to R. So P to R is space that goes up to x squared. And we know that the dimension of P to R is equal to 3 because it's comprised of only one x and x squared. And since that's equal to 3, and we have 3 elements in S, to prove that S is a basis, we just have to show that S is linearly independent. And yeah, so we've already done a linear independence question. So to prove that this set is linearly independent, we just find a linear combination of the basis of the set elements and set it to 0. And we have to show that these scalar values are equal to 0. So what we do here is that we group the values of the scalar values for the constant x and x squared. And this is equal to 0 plus 0x plus 0x squared. So what we're going to do now is compare the coefficients. So this means that if this is actually equal to 0, 2 lambda 1 plus lambda 3 is equal to 0. This is equal to 0. And this is equal to 0. So an easy way to solve this, you might have thought, is as an augmented matrix. So here we have this augmented matrix we drew up. So the way we got this is that here, so this is the coefficient for 0, x squared. So we know for the constant, that's going to be 2 lambda 1 plus lambda 3. And we do the rest for x and x squared. And then we know we have to row reduce it, because when we row reduce and see the number of leading columns, that shows whether a set of vectors is linearly dependent or independent. So if we get 3 leading columns, we know that this set is linearly independent. And as we row reduce, we do in fact get 3 leading columns, so the set is independent. So therefore, we can say that S is a basis of P to R. So for coordinate vectors, so with coordinate vectors, we want to write a certain vector in terms of as a linear combination of the basis elements. So a standard example is, say, the basis of R2 is E1, E2. And for any element in R2, so say for example 5, 4, that's equal to 5 times 1, 0 plus 4 times 0, 1. So therefore we write it as five, 4 as a coordinate vector. Since it's 5 times the first basis element, plus 4 times the second basis element. So yeah, I'll just quickly go on to an example. So let V be a vector space of all symmetric 2x2 matrices, and we have A here. So find the corresponding coordinate vector with respect to the basis. So to find the coordinate vector, we just want to find a linear combination of these three elements that equals to A. So for example, alpha times this element plus beta times this element plus gamma times this element is equal to A. The coordinate vector will be alpha, beta, gamma, like this. And a quick aside is that since we're dealing with symmetric matrices, so these elements are going to be the same, the basis for 2x2 symmetric matrices is actually only size 3, because we only have to worry about one of these. So yeah, so we want to find a vector alpha such that our matrix A is a linear combination of these basis matrices. And to calculate this, again, we go to the augmented matrix. So here we're considering each element of the matrix. So for this entry, for 9, that's going to be a linear combination of 1, 2, and 4. So that's what we get here. And we do the same for the other entries, 5 and minus 4. So we get this matrix, and then we just row reduce it. So now it's all row reduced. And then now we know that since this is alpha 1, alpha 2, alpha 3, we know that 52 alpha 3 is equal to 88. And then we just calculate the rest of alpha 1 and alpha 2, which we find to be these values. And then therefore we have the coordinate. So to check that this is the right coordinate vector is if we did a linear combination minus 29 on 13 of the first matrix plus 29 on 13 of the second matrix plus 22 on 13 of the third matrix, we should technically get A. And this is the final topic I'm going to do. So this is a Math2601 topic. So for sums of vector spaces, we define this for the sum of two subspaces, we define their sum as U plus W. So the elements of V such that they can be constructed in a way that one element is from U and plus an element from W. And in the case that these two subspaces that you're adding up, they have 0 vectors in common, we're going to call that a direct sum, which is denoted by this notation. And suppose that U and V are finite subspaces of V, then we have this formula. Yeah, and this can help determine whether a sum is direct or not, because as we know, if a sum is going to be direct, we know that this is going to be equal to 0. So if we have these three values, and by this equation we can prove that this is equal to 0, that's how we can prove that a sum is direct. So I'll quickly go over this question. So consider these two sets. So they're matrices, and this matrix is constructed from two real values, x1 and x2. And this matrix is constructed from three y values. So we want to write down a basis for W1 and W2. And so we're just going to do that via inspection. Since W1 is constructed from two values, two real values, we can just separate out the x1 and x2 to get a basis of size 2. And the same thing for W2. And the next part is find the basis for W1 and W2, W1 intersection W2. So if a vector is in the intersection of W1 and W2, it's going to have to satisfy both of these rules. And for the final bit, find the basis for the sum of W1 and W2, which includes your basis from part 2. Okay, so to find the basis for W1 and W2, we can just take out x1 and x2. And to find the basis for W2, we can take out the y1 to y3. Yeah, and like I said, to find the intersection of W1 and W2, the rule in W1 has to be true, and the rule in W2 also has to be true. So we're looking for a matrix where it can agree with both of these. And the way we're going to solve for a matrix that looks like that is to equate each entry with each other. So we end up with 4 equations. So for example, x1 is equal to y1, minus x2 is equal to y2 minus y3. And we just do simultaneous equations with these 4 equations, and we just get a couple results that x2 is equal to 2x1. And therefore, if we start off with a matrix in W1, we can sub in this information that we got, that x2 equals to 2x1, so here. And we'll find that the matrix is only in terms of x1, which means we can factor out the x1. And the basis of this intersection is just multiples of this matrix. And to find the basis for the sum of W1 and W2, if we just remember this formula, and since we know the dimension of W1 and W2, and we just found that W1 intersection W2 has dimension 1, here dimension 1, the formula tells us that the dimension of the sum is equal to 4. But if we remember, we're in the space of 2 by 2 matrices, which means that if the dimension of the sum of W1 and W2 is 4, that means W1 and W2 spans all 2 by 2 matrices. So that's what we have here. So we want to extend the basis that we found in part 2. So we want to extend the basis of W2 to 4 elements. So size 3. So that means we need to add one more element to the basis. And to pick the element that we're going to add, it's going to be an element that can't be in W2. And we just kind of use this method where we just kind of test all the standard bases matrices, 2 by 2 standard basis matrices, to see which can be constructed in W2. And we find that this matrix cannot be constructed in W2. So this is the missing matrix that should be added to the basis. So this is the end of my part. So Steve will carry on with the rest of this seminar.
Right, hey everyone. My name is Steve. I'll be taking over for the second part of part one of the seminar. Hope you guys can hear me, or I'm going to test that myself. It seems like it's working. Alright, let's get on with it. So what I'm going to cover today is linear transformations and inner product spaces. So let's get on with it. So first thing, I'm just gonna go through a bunch of revision stuff that you should be familiar with by now. So these are just the definitions of a linear transformation. So if a linear transformation is basically a function from one vector space to another, and it satisfies two conditions. If you give as input a sum of vectors, then you can just separate the sum, and you can also take out scalar multiplication. And these are just called preserving addition and scalar multiplication. And yeah, to determine whether a function like this is actually a linear transformation, we can, one option is to just check these two conditions, or there is a better way, like a slightly easier method that allows us to just combine those two conditions. So if we have a mapping from a vector space V to vector space W, then T is linear if T of x plus lambda y equals Tx plus lambda Ty for all xy in the domain and lambda a scalar. So yeah, hopefully that's all familiar. We're just gonna do sorry. Yeah, so we're just gonna do an example of this. So let's just prove that this function from R2 to R3 is a linear transformation. Let me share my screen. So what was the function again? It was Tx equals x1 plus x2, x1 minus x2 through x1. So yeah, here we can just say x is x1, x2. Okay, well, how do we show that this is linear? Well, we just apply the easier theorem that we just saw in the previous slide. So suppose x and y are in R2, and lambda is a scalar. In this case, let's just assume it's real. Yeah, all we need to do is just find t of x plus lambda y, and then show that that's equal to t of x plus lambda ty. And here, let's just say x is x1, x2, y is y1, y2. Alright, so t of x plus lambda y, well, it'll be good to just figure out the components of the sum of vectors. That would be t of x1 plus lambda y1, x2 plus lambda y2. And just applying this formula over here, we just get x1 plus lambda y1 plus x2 plus lambda y2. And the second component would be same thing, just minus. The third one is just 3 times x1 plus lambda y1. And remember, the goal is trying to get t of x to t of y. So we want this to turn into t of x plus lambda ty. And to do that, we just separate out the variables inside this massive vector we have. So we want t of x first of all, and we can just get that by taking out the x1 plus x2 and x1 minus x2 and 3x1 out of this vector. And that would result in x1 plus x2, x1 minus x2, 3x1 plus what's remaining. So on the top we'll have lambda y1 plus lambda y2, lambda y1 minus lambda y2, and 3 lambda y1. And if you look at the formula, this is just t of x. And the second one, you can take out the lambda, and it will be lambda ty. And so yeah, because of this and the previous theorem, we see that T is a linear transformation. All right. Okay, so there we have it. All right, so there's two kind of important sets involved or related to a linear transformation, and they're called the kernel and image. The kernel of T is the set of all things that make T zero. So like all the inputs X, so that T of X is the zero vector in W. And the image of T is the set of all possible outputs of T. So like more formally, the kernel of T is the set of all V in V, so that T of V equals zero. The image of T is the set of all T of X's for every X in the domain V. And it turns out that the kernel and the image are also vector spaces under the field F as well. So the kernel would be a subspace of V, image would be which would be a subspace of W. The dimensions of the kernel image, they have special names called nullity and rank, respectively. And it turns out that for linear transformation on finite dimensional vector spaces, if you add these two dimensions, you get the dimension of the domain. And that's called the rank nullity theorem. And so the conditions are we have T, which is a linear map from V to W. V is finite dimensional, and if that's true, then the rank plus the nullity equals the dimension of V. And this is actually really useful for determining whether a linear transformation is invertible because of this following theorem. So if we have a linear transformation, same kind of thing from vector space V to vector space W. If we have the dimension of V and W the same, let's just say n, then these following three statements are just like different ways of saying the same thing. They imply each other. So nullity equals zero, that implies rank equals n, and that also implies T is invertible, and invertible implies nullity zero, and like etc. And so you can kind of see that this is really useful because all we need to show, all we need to do to show that T is invertible is just to show something like simple like this, the nullity equals zero. If the nullity isn't zero, then T is not invertible as well because these are equivalent statements. All right, so let's try this proof here. It's from the 2601 paper, so the proofs are in the paper. Okay, so let's say S is a fixed P by P real matrix, and let's define a linear map T on this space of P by P matrices by T of A is just multiplying S by A. So show that rank T is P squared, so the rank of T is P squared if and only if S is invertible. Okay, well, how do we do this? Well, it's an if and only if statement, so let's just try prove two different directions. Let's try the forward direction, so which is if rank is P squared, then S is invertible. All right, so let's suppose the rank of T is P squared. And what does that mean? Well, just by definition, rank is the dimension of the image. So the dimension of the image of T must be P squared. But the thing is, the codomain of T is P squared. Like if we multiply P by P matrices with each other, then we get P by P matrices. And so this forces the image of T to be the entire space of P by P real matrices. Because remember, the image is a subspace of the codomain, but the codomain is already P squared dimensional and the image is P squared dimensional. So a P squared dimensional subspace of this would be just the space itself, yeah. Yeah, so the image of T is just the entire space of P by P matrices. And what that implies is that every P by P real matrix is a possible output of T. It's like the image is this, so that's saying, the set of all outputs is the entire space of P by P matrices. And suddenly IP, the identity P by P real matrix, that's definitely inside the image. So by definition, there should be some matrix Q, some input that we give to T so that multiplying or applying T to Q gives us the identity matrix. And that just translates into there exists a matrix Q, so that SQ is I, the identity matrix. Well, that's pretty good for us because that's saying Q is the inverse of S, and S is invertible, therefore. So that's like the first forward direction proof. So we just went from rank equals P squared to S is invertible at the end. And again, this is an if and only if statement, so we go backwards as well. We have to prove the reverse direction. So let's try go the other way. Suppose S is invertible. Okay, then we had that theorem before saying that the nullity, if the nullity is 0, then T is invertible. And in this case, that theorem works because the dimension of the domain and codomain are the same here. That's really important. All right, so we want to show nullity of T equals 0. And to do that, remember nullity is the dimension of the kernel, so it makes sense to try and find the kernel. But the thing is, the kernel is the set of all things that make T 0. And so if we assume that, like let's say A is inside the kernel, then we want T of A to be 0. So in other words, S times A equals the 0 matrix. But if we have that, since we assume that S is invertible, multiplying by S inverse, that gives us A equals the 0 matrix. And what this means is that no matter because the choice of A in the kernel was like very arbitrary, it doesn't matter what we choose, it's always going to be the 0 matrix, which implies that the 0 matrix is the only thing in the kernel. And because of that, the dimension of the kernel is actually 0. This is a 0-dimensional subspace, the trivial one. And so by the previous theorem, T is invertible. And that's good for us, because if T is invertible, the rank of T must be P squared. All right, moving on. Let's talk about matrix representations of linear maps. It turns out that, for any finite dimensional linear map, you can just represent it as a matrix multiplication. And so here's the theorem. Let's say T is linear from V to W, and let's say B is the basis for V, and C is the basis for W. Then there's always a unique matrix A, so that the coordinate vector of T of V respect to C is equal to A times the coordinate vector of V respect to B. Remember, these are general vector spaces, so we gotta have these coordinate vectors to make sense of this matrix multiplication. Like think about like if V and W were the space of polynomials, then yeah, we can't just like leave these coordinate vectors out. So essentially A is just a way of going from the coordinate vector of V respect to B to TV respect to C. And just for notation, we're going to denote this A by T with B on top, C on the bottom, as the matrix representative of T for the respective B in the domain, C in the codomain. Very important to remember, the domain is always at the thing at the top, and the basis for the codomain is always at the bottom. Okay, so the question is, how do we find the matrix representation of any linear map? Well, there's a simple strategy, very simple to say, in fact. First, we need to choose a basis first for like the domain and the codomain, say B and C. And if P is the dimension of V, then we should have P vectors in B, right? Because that's the definition of dimension. So let's just say the basis vectors for the domain is V1 all the way up to Vp. Then the process of finding this matrix representation is just applying T to each of these basis vectors, finding their coordinate vector with respect to C, so the basis on the codomain, and those guys will form the columns of A. So this thing here, coordinate vector of TV1 that'll form the first column of A, TV2, coordinate vector C, that's the second column, and blah 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 blah, you get P columns, with the last one being the coordinate vector of T or VP respect to C. So yeah, as I was saying, this is a simple strategy to say. Sometimes it might be hard. If we have the standard bases, it will be pretty easy because finding coordinate vectors on the standard bases are pretty easy. But for more complicated bases, it can be pretty difficult to find coordinate vectors, and so we need a different approach. So the essential idea is that we like to use the standard bases because it's simpler. So we want to convert to the standard bases, do the transformation there, and then convert back to the complicated bases. And this is described by this triple matrix multiplication here. So let's say T is just from V to W, it's a linear map. Let's say S1 is a standard basis for V, and S2 be the standard basis for W. Then the matrix representation of T with B in the domain, C in the codomain, that's equal to this big matrix product here. And all this is saying is that we apply this one first. This one is the change of basis matrix because the ID, it's like ID of V, which is the V. We convert a vector from with respect to B into something with respect to S1, the standard basis. We apply the transformation and like convert it to the standard basis for W. And then we convert that vector back into a vector with respect to C. So it's inverse thing, which swaps the order of these two. And the thing about this, the really good thing about this method is that these three matrices are really easy to find because they always deal with standard bases. Okay, let's do an example of this. So we have this linear transformation here. It's the same one we saw before. Let's just say B is a basis for R2, just these two vectors, not the standard basis, and C a basis for R3, and again, not the standard basis. The task is to find a matrix of T with respect to B in the domain and C in the codomain. Okay, so these bases, they're not very pleasant to deal with. They're not the standard bases, as I said. So let's use the alternative approach, which is this. Okay, so yeah, S1 and S2 are the standard bases of R2 and R3. So like the 1, 0 and 0, 1 vector, and the 1, 0, 0, 0, 1, 0, and 0, 0, 1 vectors for R3. Here, the ID B S1, so like B in the domain, S1, the standard basis in the domain as well. This is just the matrix whose columns are the vectors in B. Because remember, to find like the original method that was simple to say was that we have to take each basis vector in the domain, apply this transformation, the identity transformation, which does nothing in this case, and convert it to a vector with respect to the standard basis S1. But the standard basis S1, that's just, that makes it really easy. Like the coordinate vector is essentially just the same as the original vector. And so that just ends up with the effect of having the columns just as the vectors in B. And similarly for this one, it's just the matrix whose columns are the vectors in C. So like we literally just write down the vectors in B, but like as columns in the matrix, and same thing for C. Also, to find the middle one in the multiplication, this one, this is just, again, applying our strategy before, the simpler non-alternative strategy. We take each basis vector in S1, which is just E1 and E2, the 1, 0, and 0, 1. We apply t to it and convert it so that it's with respect to S2. But again, S2 is just the standard basis for the R3. So it's like the corner vector is just the same as these two. So we just find these, t of E1, t of E2, and it turns out to be 1, 1, 3 and 1, minus 1, 0. We just chuck them as cols. And that's what we get for t, S1, S2. And yeah, before we just put all of this together, we have to find the inverse of this matrix here because that was what the formula says. And using first year methods, just like augmenting it with the identity matrix on the right and doing some row reduction until the left matrix becomes the row echelon form, reduced row echelon form, we found out the inverse is this. Or you can just use a matrix calculator, I guess. And just putting it all together, we just chuck all of those components in the formula, and the matrix ending up from that turns out to be this. Okay, I'm not going to go through the computation here because I can't be bothered, and it's just tedious. Alright, moving on, let's deal with invariant transformations, and this is a 2601 only topic. So what are these? Well, we need a linear map first from the same domain, codomain. So let's say T is linear from V to V, and that X is a subspace of V. Then we say X is invariant. It's an invariant subspace under T if T of X is a subspace of X. So it's like, this is like the more formal way of saying that applying T to any vector in an invariant subspace, X, results back inside a subspace of X. Okay, so let's have a look at this different linear map here. It's just defined by this matrix multiplication. So yeah, T goes from R3 to R3, T of X is AX, where A is this 3 by 3 matrix. Let's define a subspace W of R3 as just the span of these two vectors. Let's try to prove that W is invariant under T. Okay. So yeah, let's just suppose Y is in TW. Then Y equals AX for some X in W, because that's what it means. T of W is just the set of all T of X's where X is in W. So yeah, Y equals AX for some X in W. And by definition of W, because it's a span, that means there's some scalars lambda and mu, so that Y is lambda A of the first vector in the span, plus mu A, the second vector of the span. Yeah, because this is I kind of put two steps here in one. This is really saying since X is in W, X is equal to lambda times this plus mu times this, but we're applying A to it and just splitting this up. We can just compute these though. Let's just give them names, V1 and V2. A of 0, 1, minus 1 turns out to be this. Just do A of the second vector in the span, we get V2 equals this. Yeah, these are just names I've assigned because it's more convenient that way. And so, yeah, we have lambda y1 plus mu v2 for y. So to prove that we have a invariant subspace here, we have to show that y ends up back in W. And so all we need to show is that v1 and v2 are in W. And because if we do that, then v1 and v2 are in the span of like these two vectors. I mean, yeah, these two, the basis in the vectors in the span definition of W. And y would be a linear combination of those vectors in that span, so that has to be in the span again. Yes, so that's all we need to do. We need to show that v1 and v2 are in W. We can do this by inspection, just like looking at -4, -1, and seeing how it can be formed from 0, 1, -1, and 2, 1, -1. Or we can do row reduction, which will be longer, but yeah. For the sake of time, the inspection method is here. So V1 ends up being 0, 1, -1 minus 2 times 2, 1, -1. And I guess in this case, it's actually easy to do it by inspection because the only way you'll get -4, -4, -4, -1, 1 from these two vectors is, well, you would get -2 times this one because there's no way of getting the -4 from the first vector here. So you just put it in there and then just, that would be, it'll somehow fall out nicely. Same thing for V2. Yeah, V2 again, we need this -6 from somewhere. And we're definitely not going to get it from this vector, so we got to do -3 times this vector here. And yeah, it just falls through. You just like do the -3 times 2, 1, -1 and just fix it up. Make up for like the remaining parts in V2 by taking a multiple of the first vector here. But yeah, all this is saying is that V1 and V2 are in W, so Y must be in W as well. And therefore, since Y, we just assumed it was in T of W, T of W is a subspace of W. All right. Next, we're moving on to similarity. So, sorry. Okay. All right. So yeah, moving on. We're going to talk about similarity. We say that matrices A, B in the P by P matrix space on some field. We say those are similar if there's an invertible matrix P so that B is P inverse AP. And this actually represents that A and B are similar if they represent the same linear transformation but with different bases. So there are properties called similarity invariance which hold whenever A and B are similar. And for example, well, there's 3 examples here, 4 examples. The rank of similar matrices are the same, nullities are the same, the traces are the same. Trace is just the sum of the diagonal elements, and the determinants are the same. So yeah, this is like saying if A and B are similar, then all of these equalities hold. The converse doesn't hold for these because they're not a complete similarity invariant. So even if all of these properties hold, that doesn't imply similarity. We can have non-similar matrices that satisfy all 4 of these conditions. What's useful about this though is that it's really easy, what makes it really easy to check whether A and B are not similar. So let's try it on this example. So let's just try to show that A and B are not similar. And the logic here is to use the contrapositive. So if you look here, it's like if A and B are similar, then all 4 of these hold. So the contrapositive would be if any of these don't hold, then A and B are not similar. Right, so all we have to do is show that one of these similarity invariants don't hold. Let's just go through them one by one from like the easiest one first. So trace, in my opinion, is like the easiest one to check. Is add up the diagonal elements. The trace of A is 1 minus 1 plus 2, that's 2. The trace of B is minus 2 plus 3 plus 1, that's 2. They're equal, so that doesn't really help us. We're looking for a similarity invariant that isn't the same. So let's check the determinant. Determinant here is actually easy to find because of these zeros and the zeros here. The determinant of A would be 1 times minus 1 times 2 minus 1 times 6, and that actually gives us 4. And similarly, the determinant of B, this is an upper triangle matrix, so you can just multiply the terms here. You get minus 6. And so you can see that the determinants of A and B are not the same. And so by the contrapositive, A and B can't be similar. All right, that's it for linear transformations. I'll be moving on to inner product spaces. Okay, so inner product spaces. Inner product. What is an inner product? Well, it's really just a generalization of the dot product in Rn. It's like we're trying to bring the same sort of idea to more general vector spaces, like vector spaces of polynomials, say. So let's say V is a vector space along with its respective field F. An inner product is really just a function that takes in two vectors in V and goes to F with, and it has to satisfy these four properties. So these first two properties, it's really just saying this inner product has to be linear in the second argument. So y plus z in the second argument, you can split into two inner products based on that addition. Same thing for a scalar multiplication. You can just bring the lambda outside for the second argument. But there's two more properties. The third one says that if you swap the order of the arguments, like x and y, you have to take the conjugate. And this is just to deal with uh, when the field is complex. Also, finally, the dot product, the inner product of a vector x with itself must be non-negative, and it can only equal 0 if x is 0. So the only way for this to be 0 is if the x is a 0 vector, and if x is a 0 vector, then x inner product x is 0. And so as I said, it's a generalization of a dot product. So there's a sense of orthogonality based on inner product as well. So we say if the inner product is 0, then we say the vectors are orthogonal to each other. So like this is similar to x dot y equals 0 in Rn. And we use the same kind of symbol, this perpendicular symbol, to denote that. There's also a sense of orthonormal vectors. A set of vectors S, we have n over here. We have n of these vectors, v1 to vn. We say that's an orthonormal set if for every pair of vectors here, the inner product of vi, vj is 1 if I equals j and 0 if I is not j. So another way of saying this is S is orthonormal if the vectors are size 1. So the vectors inner product with each other is 1, and that they're orthogonal to each other. So if these are different, then the inner product is 0. I mentioned size here. This really should say, like, this is really just a norm. So like, if you take inner product with something with itself, then you get the norm squared. Okay. Also, we get the projection from Rn as well. It generalizes to, generalizes with inner products. If we have y and x inside a vector space, we say the projection of x onto y as this. This is like very, very similar looking to the projection on Rn that you might have saw. And the thing is, for this, the order actually matters because the field might be complex and like we have to deal with complex conjugates in that case. And so yeah, this formula is defined so that x minus the projection of x onto y is perpendicular to y. And let me just show you how that works. The projection, like if we have, say, two vectors like this, say x and y, like that, all the projection is like the component of x going to y. So you kind of like extend y here. You kind of see that the component of x going in the y direction is like this part here. Use a different color. So this green thing is the projection of x onto y. So if you take away, like if you compute this vector, x minus projection of x onto y, then just looking just like visually, that'll be the vector with the head at here and the tail over here, which is the vector going this way. This is x minus projection of x onto y. And so we can see that they're like perpendicular. X minus projection of x onto y has to be perpendicular to y, which was what I was saying here. Yeah. Right, and as I said before, this is very, very important. The order of the y and x in the numerator here, the inner product, is very important for a complex inner product due to that complex conjugate. Okay, so if we have a vector space equipped with an inner product, we call it the inner product space. And it turns out that for finite dimensional inner product spaces, they always have an orthonormal basis. The Gram-Schmidt process is a process of finding such an orthonormal basis given some basis, like any old basis. So here's how it goes. So we need a basis, as I said. Let's just say V1 all the way up to Vn is an orthonormal is a basis for whatever vector space we're talking about. I mean, in a product space. And so given that, an orthogonal basis is these W vectors here, where the W vectors are found in this way. We set W1, the first one, to just equal the first basis vector. The second one, we get the we take the second basis vector and minus its projection onto W1, so like the previous one. W3, the third orthogonal basis vector, we take V3 and take its projections onto the previous W vectors we saw. So like V3 onto W1 and V3 onto W2. And so like you just keep repeating this until we get to the last one, Wn. We take the last basis vector and take away the projections of it onto the previous W vectors we found. And so yeah, this is an orthogonal basis. To get an orthonormal basis, we just rescale each vector so that they're size 1. Okay, so let's try this question here. It's just applying Gram-Schmidt process. Let's say W is a subspace of R4 that's a span of V1, V2, and V3 over here. Task is to find an orthonormal basis for W, and this is under the regular dot product. So like this orthonormal, like the definition of orthonormal depends on the definition of a inner product. Okay, let's share my screen again. W was the span of V1, V2, V3, where V1, let me just copy down the vectors for convenience. V1 is 1 minus 100, V2 is 0210, V3 is 2011. Okay. So yeah, we want to find an orthonormal basis for W. So we have to apply the Gram-Schmidt process on here. For the Gram-Schmidt process, we need a basis first, but in this case, we already have a basis, V1, V2, V3. So the orthonormal basis is going to be W1, W2, W3, where the first one, we set it to the first basis vector, 1 minus 100. The second one, we take the second basis vector and take away its projection onto the previous W vectors. In this case, the only one is W1. So like projection of V2 onto W1. And that's 0210 minus, we're dealing with the standard dot product here, so W1 dot V2, W1 dot W1 times W1. That's 0210 minus, well, what's W1 dot V2? That's these two vectors here. That would be 0 plus minus 2 plus 0 plus 0. So that's minus 2 on the top. W1 dot W1, that's just 2. W1 is 1 minus 100. And that gives us 0210 minus or plus 1 minus 100. That's 1110. Yeah, so that's the second orthogonal basis vector. Now we do the third one. The third one, again, we take the third basis vector we have, and we take away the projections of it onto the previous W vectors. So projection of V3 onto the previous one, as well as the other previous W vector. Right, and what is this? We just compute it. V3 is 2011. Let's just write down the formula. W2 dot V3 W2 dot W2 W2. That's 2011 minus, what's W1 dot V3? That's these two over here. That's 2 plus 0 plus 0 plus 0. That's 2 again. So that's 2. We saw that W1 dot W1 was 2. And W1 was 1 minus 100. I think. Yep. The second one here, W2 dot V3. That's these two over here. That's 2 plus 0 plus 1 plus 0. That's 3. That's 3 on W2 dot W2. That's 1 plus 1 plus 1. That's 3. And W2 is 1110. So this is just 2011 minus 1 minus 100 minus 1110, which gives us 0, 0, 0, 1. Okay, so what this is saying, we found the orthogonal basis vectors. So 1 minus 100, 1110, and 0001 form an orthogonal basis for W. But we wanted a orthonormal basis, right? And the way we do that, we just divide each of these vectors by the lengths. So the length of the first one, that's 2, so I mean root 2, so we just like divide by root 2. The length of the second one is root 3, so divided by root 3. And the length of the third one is already 1, so we just divide it by 1, which just does nothing. So this is an orthonormal basis for W, using the Gram-Schmidt's process and then rescaling. Okay. Hopefully that makes sense. Yep. Okay. So we're talking about projections of a vector onto another vector. There's another kind of projection onto subspaces. So a vector onto a subspace instead of another vector. And before we get onto that, let's define what an orthogonal complement means. So if we have a W, which is a subspace of a vector space V, then this W perp is going to be called the orthogonal complement of W, and that's the space of all vectors X in the entire vector space, which are orthogonal to every vector in W. Let me illustrate that for you. So, yeah, let's say we have, let's just talk about R3 here. Okay, and let's say, what's a good subspace to talk about? Let's just talk about a plane. How do I draw this? Yeah, a plane through the origin. Okay, well, Yeah, that's a perfectly fine two-dimensional subspace of R3. The orthogonal complement of this would be all the vectors perpendicular to every vector in this plane, which would be sort of the line like this. It's like the one-dimensional subspace that's like perpendicular to the plane here. And that way every single vector on this like green line is going to be perpendicular to every single vector on this plane. Okay, so that's what the orthogonal complement means. So for any finite dimensional vector space V and any subspace W of V, it turns out that W, the direct sum of W and W perp, the orthogonal complement, gives you the space back. And again, you can kind of visualize that from this example here. That's saying if you add up, if you take the direct sum of these two vector spaces, you get the entirety of R3, which makes sense because for any vector, like if we had like any vector like here, like then we can always kind of represent it with like a component of x inside the subspace, the two-dimensional one, plus another vector from its orthogonal complement. And we can only do this uniquely. It's a direct sum. And so for any, so this means that for any vector x in this finite dimensional vector space, you can express it uniquely as x equals a plus b, where a is from the subspace and b is from its orthogonal complement. And here's where the definition of projections onto subspaces happen. So if x has this form here, so like we uniquely represent it as a sum of a vector in W and another from its orthogonal complement, then we say this is A here. A is the projection of x onto the subspace W, and B is the projection of x onto the orthogonal complement of W. So it's really like the intuitive way of thinking about this is like this part here. Let's say the red one is W and the green one is W complement. This part here, that's the component of x inside the subspace W, kind of. It's like a really good intuitive way of thinking about it. This is projection of x onto space W. And the other one here, it's like its remaining part. So like the component of x going perpendicular to the subspace W. This is projection x onto W perp. Yeah, hopefully this illustration gives you a better intuition. And so again, similar to the first projection we saw, we see that if we take away the projection, like if we have x and take away its projection onto a subspace W, then that has to end up in the orthogonal complement of W. Again, like have a look at this again. So this is a very good example. If we take away x, like if we do x minus the projection of x onto the subspace W, we get this thick green vector. And that's going to be in the like this. It's only going to be in the W complement, right? It's like it's the component that's like perpendicular to W. Yeah. Let's do this example here. So this is from 261 again. I've changed the question slightly. Let W be the span of V1 and V2, and that's going to be a subspace of R4. And V1 and V2 are defined by these two vectors here. The problem is to find the projection of x, which is just 1 over O, onto W with the usual dot product on R4. Okay. So we want the projection of x onto W, right? So that's what we want. Let's just like give it a name. Let's just say y is that projection that we want. Then y must be lambda v1 plus mu v2 because the projection of x onto the subspace W, that's the component of x inside the subspace W. And so it makes sense that y must be in W. So since y is in W and W is the span of v1 and v2, y must be a linear combination of those v1, v2 vectors. And also, it must satisfy that x minus y is inside the orthogonal complement. And again, that's like, just think of this as just sub in the projection here, and we get that identity we saw in the previous slide. So x minus the projection of x onto W, that must be in the orthogonal complement. So the thing is, we have a basis for W. We just need to make sure that x minus y is orthogonal to both v1 and v2, right? Because for this to happen, we need x minus y to be perpendicular to all vectors in W. But every vector on W is a linear combination of v1 and v2. So if x minus y is orthogonal to both v1 and v2, then it should be orthogonal to anything, like any linear combination of v1 and v2. Right, so this is how we're going to solve for lambda and mu. This gives us two equations. So we want to, the two conditions come from these two. So we want x minus y to be perpendicular to v1 and v2. I mean orthogonal, same thing. And so these conditions, these give us two equations in lambda and mu. Remember, x was just 1, 0, and y was a linear combination of v1 and v2. So it was like lambda v1 plus mu v2. We know these vectors v1 and v2. So the only unknowns we're going to get from these two equations are these two. Two equations, two variables. That's pretty easy. We just use simultaneous equations. So we solve it simultaneously, and I left out a bunch of details here, but you eventually get that lambda and mu are 2 on 11 and 3 on 11. And so since we said y is the projection of x onto W, and we said that was lambda v1 plus mu v2, we just get that the projection of x onto W is this linear combination, which happens to be this vector here, if you do the computation. We know what v1 and v2 are here. Just sub it in. Okay, hopefully that makes sense. Let's move on. Yeah, so let's move on to a new topic called QR factorization. So what QR factorization is if we have a full rank P by Q matrix, so it's a matrix with linearly independent columns, you can factorize it into two matrices, an orthogonal P by Q matrix, Q, and R, a big R, an invertible Q by Q upper triangular matrix. And this is way better if we visualize it like this. So the QR factorization for this is we have the Q matrix, the big Q matrix. It's an orthogonal matrix, so these Q1, Q2, blah, 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 QQ. Those are going to be orthonormal. And we have this big R matrix, which is formed in this complicated way. A lot of stuff to solve it. Here, good thing about this theorem, it gives us a way of finding all of these vectors, or all of these terms. Here, the W vectors along this diagonal, these are just the vectors found by applying the Gram-Schmidt process on the columns of A. The QKs are the normalized vectors of these, so like just rescaled versions of the W vectors, so that they form like an orthonormal basis. The A's are the column vectors of A, so AK is the kth column of A. And if we have that, then the QR factorization, we just sub in all of those, and we get our desired result. So let's try a QR factorization of B here. It's just a 4 by 2 matrix. And here it is full rank because the columns are definitely linearly independent. So the first step we apply Gram-Schmidt to the columns of B. So there's only two here, so that makes it makes our life a bit easier. W1, we just set it to the first vector. This is 1, 1, 1, 1. For the second one, we take the second column, like kind of like the second basis vector, and take away the projections of it on projection of A2 onto the previous W vectors. And in this case, it's only W1. And that gives us A2, which is 1, 2, 4, 5, minus 4 plus 5, that's 12. And W1 dot W1 is 4. And we just multiply that by W1. And just computing that, we get minus 2, minus 1, 1, 2. So these are the W vectors we wanted here, which is good. To find the Q vectors, we rescale these. We normalize, so like divide the W vectors by the lengths, and we get these two vectors here. The final thing we need is Q1, A2. And that's because we only have two of these W vectors here. So like our matrix, like our R matrix was just like end over here. Like it will just be 2 by 2. So the only like inner product we need to find here is Q1 inner product A2. Well, dot product, because in our question, we're just dealing with the dot product. So yeah, we just calculate this. We know what Q1 is. We know what A2 is. A2 is just the second column of B. And that just gives us, well, it should be a quarter here. Oops. That gives us 3. And so the Q of factorization, we have this. So we just put in the Q vectors. We put the norms of the, or lengths of the W and W2 vectors on the diagonal and put the inner product here. And Q1 is half, 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 half. Q2 is minus 2, minus 1, 1, 2, just like all divided by root 10. The length of W1, you can just find it here, 2. It's like hiding over here. Length of W2 is root 10 because we divided Q2, divided W2 by that to get Q2. And the inner product finally, yeah, this is 6. Never mind, yeah, it's not a quarter, it's 2, and it should be 6 here. So about that typo. So yeah, that should be a 6 here. Yeah, so that's our QR factorization. We see that R here is a invertible 2 by 2 upper triangle matrix, and this is a orthogonal matrix 4 by 2. Okay, moving on. Let's talk about adjoints, and again, this is MATH2601 stuff. So the adjoint of a linear map T from V to W, we call it T star, and it goes the other way, W to V. It's really a way of kind of like switching around the order of the inner product. So if we take inner product of W and TV, that's equal to the adjoint of W inner product V. Like just like kind of like taking the T out and applying to the other one. And so yeah, we just call T star the adjoint of T. There's some useful properties of adjoints. If you take the adjoint of the sum of two linear maps, you can just add up the individual adjoints. If you have a scalar multiple of a linear transformation and then adjoint that, you have to multiply the adjoint of T by the conjugate of A, alpha. If you take the adjoint of the adjoint, you get the original linear map back, and the composition of linear maps, their adjoint is kind of taking the composition of the adjoint in the other way. So it's like similar to like inverse, I guess. All right, so let's try apply the concept of adjoints on this example here. It's a very thick question. Let's say V is the space of degree 2 or less polynomials, real polynomials. I should say real coefficients. And let's just say W is another vector space, it's just R. Let's define these wacky inner products, not the usual ones. inner product of two polynomials as -1 to 1, the integral of p by p times q, and the inner product of two real numbers as is 4 times their product. Let's define a linear map that goes from V to W by T of P equals P minus 1. Remember P here, we give T, like the domain of T is a space of polynomials, so this is a polynomial. And we just want T of P to be just applying -1 to that polynomial. Our task is to find an explicit formula for the adjoint of T. Right, so T star of V, say, V a real number. And here we're just given a hint, just a convenience, so we don't have to like compute integrals ourselves. We just assume that like the integral of -1 to 1, t to the n, is 2 on n plus 1 if n is even, 0 if n is odd for non-negative integers n. Okay, so how do we tackle this? Remember, the adjoint is a linear map that satisfies this equality for all u in real numbers and, well, this is w actually, and p in v, which is the degree 2 polynomials or less. So we want a linear transformation that satisfies this. We know what t is already. The thing is, we have to first note that t star of a real number, that should give us a polynomial, a degree 2 polynomial or less, because the adjoint goes from the adjoint goes the other way. So like gives us a real number, takes in a real number, gives us a polynomial. So to find an explicit formula for something like this, we should just let t star u be a polynomial so that it's just q0 plus q1t plus q2t squared. These three coefficients are, well, we need to determine them in terms of u. That's the goal. And so, we want to make sure that this equality holds. Let's actually see what those two inner products look like. And let's just assume, p is an arbitrary polynomial, po plus p1t plus p2t squared. If we evaluate the first one here, that will be just utp, which is, remember, this is the inner product on w, which is the real numbers. We take 4 times the product of these two real numbers, u and p of -1. And that gives us 4u times po minus p1 plus p2. It's like sub in -1 for t in this equation. The second one is much more involved. We want to take the inner product of the polynomial t star u with p. And remember, that one is the integral from -1 to 1 of the product of those two polynomials. And it's through painful expansion of this product and just keeping only the even power terms, because the odd powers are ignored, like the interval will be 0 because we're on an interval that's like around 0, like a symmetric one. We eventually, after much effort, get this. We get that this thing here is this massive equation here. Okay, so remember, our goal is to find q0, q1, q2 in terms of u, because we want an explicit formula for t star u. Like, we can't just have these arbitrary, like, we need the q0, q1, q2 to come from u. That's like the only thing that determines the coefficients of the polynomial. And so to get that, we have to equate coefficients of PO, P1, P2 in the two inner products we just calculated. The reason for doing that is because, well, firstly, the intuitive way is we can't really equate the coefficients of Q, because the coefficients Q0, Q1, Q2, because they don't apply, they don't appear in both of these formulas. The other reason is that we can't change P0, P1, P2. They're like fixed. Like, the thing that we're able to like represent in terms of u are the Q1, Q2, and Q0. say it makes sense to equate coefficients on P0, P1, P2. We don't really have to do that for this one. We should do it for this one. So like group all the P0s together, P1s together, and the P2s together. And then equate those coefficients to the coefficients here. Okay, so this is just the expression we found before. I just copied it here. Just grouping the P0s, we should get 2QO plus 2/3 Q2. So that's all the POs. Plus 2/3 Q1 P1, 2/3 Q1 P1, and P1 doesn't appear anywhere else. And then finally, 2/3 Q0, 2/3 Q0 times P2 plus 2/5 Q2 times P2. So this is like how many P2s we have. Now we compare coefficients of P0, P1, P2 over here. This was the left-hand side. And we just read off. So the coefficient of PO is 4U on here, in here, and it's 2Q0 plus 2/3 Q2 on this side here. That gives us, well, this equation. Similarly, we just equate the coefficient of P1, we get this, and same thing for P2, we get this. Now, you can kind of see here, Q1 only appears in this equation, and we can like straight away get it. Q1 will just be minus 6U here. For the other two, we have two equations, two variables, so we just solve simultaneously. So yeah, this is just the working out for that, and the point is that we eventually get Q2 is 15U and Q0 is minus 3U. And so we have the three things now. We have Q0, Q1, and Q2 here. That was the formula for T star U we wanted. So T star UT is Q0 plus Q1T plus Q2T squared. We just sub those in. And yeah, it's just making it nicer, just factorize it. Factorize the 3U out. So there we have it. That's the formula for the adjoint of T. Alright, moving on. Types of maps. This is again a 2601 only topic. So here's some definitions. Let's say T is a linear map from V to V. We say T is unitary if the adjoint of T is equal to its inverse, Hermitian if the adjoint of T is just T, and isometric if the norm of TV is equal to the norm of V for all vectors V inside V. So this is like another way of saying this is T is an isometry if it preserves norms. Now, when we talk about these kind of maps, we usually only deal with the standard inner product. And so what I mean by that is, well, like, you know how the adjoints, that depends on the inner product, like being able to like switch around the places of T. We always deal with the standard inner product on like the vector space we're talking about. And in this case, it turns out that the adjoint of T for like when dealing with the standard inner product is just represented by the conjugate transpose. So if A is a matrix of T, then the matrix of T star is just the conjugate transpose. You can just assume that. And we also have a theorem here. Being unitary and being an isometry, they're just equivalent. So a linear map is an isometry if and only if it's unitary. So these two are just the same thing. Okay, so let's try this simple question here. We have a linear map going from complex vector spaces, and they're defined by T of WZ equals 2Z minus W. And we're dealing with the standard inner product. The question is T isometric or Hermitian, or both? Well, to check whether T is isometric, we just check whether it's unitary because of the previous theorem saying that they're equivalent. So we just need to check whether A star is A inverse. And remember A star here, because it's the standard inner product, is the conjugate transpose. By the way, I should mention what A is. A is the matrix of T, and it turns out to be O2 minus 1, 0, because if you apply WZ multiplied by WZ on the right here, then you get 2Z minus W. And to check that this equality holds, instead of finding the inverse, which honestly isn't too bad, but like pointless in this case, we just check whether the multiplication is the identity matrix. And yeah, again, remember, we're dealing with the standard inner product, so the adjoint is just the conjugate transpose. If we do that, just multiply those, we get this matrix here, and that's definitely not the identity, so T is definitely not isometric. I mean, it's not unitary, so it's not isometric. And it's also not Hermitian, because for Hermitian matrices, Hermitian linear transformations, we need A star to equal A, but it's definitely not in this case. Like A star is this one, A is this one, and just look at it, it's different. All right, that's it for types of maps. That's more useful in like the part 2 of this revision seminar, which will be happening in a few days. So the final topic I want to cover is method of least squares. So what is this? Well, sometimes we have the situation where we're solving a system of linear equations in this matrix vector form, but there's fewer unknowns than equations, or like more equations than the variables, so like it's kind of overdetermined. So in general, there's no exact solution, because when we try to solve for it, we'll end up like contradicting ourselves because of like because of the fact that there's too many conditions. But we can still find like the next best thing closest to the solution in the least squares sense. And so here's like the formula for that. The least square solution to this system of linear equations is a solution to the normal equations, which is this. The A star times A times X equals A star B. Just like multiply A star on both sides. And we want the solution to that. And again, when we usually deal with this, we always talk about the standard inner product. So this is just the conjugate transpose. And for MATH2501, I don't think you deal with complex vector spaces, so the conjugate transpose is just the transpose. Okay, so yeah, all we need to do is just solve this equation. Okay, so yeah, that seems like pretty abstract stuff, but all it's saying, it really just turns out to be finding kind of like lines or like curves of best fit to points that represent that matrix. Let me just illustrate that here. So find the line that best fits in the in the least square sense to the points -1. Just write it down. -1, 3, 1, 2. Actually, I'll just show it on the slides. Okay, let's just try to find the line that best fits the least square sense to the points. Well, these 4 points here. So we want a line, right? So the line is going to have an equation of this form. It's just intercept plus gradient times x. And we want this to satisfy all of these. Obviously it can't, we'll end up contradicting ourselves. But we just like, kind of want the next best thing. And if we represent all of these conditions here, we can kind of, we can rewrite it as this matrix equation, matrix vector form. So like A minus B equals 3, that's the first one here. A plus B equals 2, -1 is A, and A plus 2B is 4. This is like rewrite it in this form. And the line that best fit in the least square sense is really just the least square solution to this overdetermined system here. And all we need to do is we just multiply both sides by A star, which is the conjugate transpose. We only have real numbers here, so we just take the transpose of this, just like put it on the left, also multiply the right hand side by it, and we get this equation. We get 4228 AB equals 87. How do we solve that? Well, you can either do row reduction, I guess, or just take the inverse of that 2 by 2 matrix, which is easy. Yeah, so just multiply the inverse of 4228 on both sides. The inverse of 4228 is just switch around the diagonal elements and make the anti-diagonal elements negative, divide by the determinant, and you eventually get that it's this vector here, 25 on 14 and 6 on 14. So the line of best fit is, yeah, you just read off the coefficients. Like this one, the first one was supposed to be A, and the second one was B. So you get 25 on 14 plus 6 on 14x, which is 3 on 7x. So yeah, that's just the method of least squares to find the line of best fit, well, kind of like the line of best fit. You can actually do this. Say like if this didn't have to be a line, right? We can replace this as like a quadratic to find the parabola of best fit that best fits these 4 points here. And we'll just get like a bigger matrix, a 4 by 3 one in that case, because we'll have like a cx squared term maybe. And yeah, but it's the same idea. Like we just apply or multiply both sides by whatever matrix we have, transpose it, solve that instead. We would have gotten a 3 by 3 matrix probably, and the inverse might have been more involved. But yeah, we can get there in the end and get like a parabola of best fit instead. Again, it also doesn't have to be parabola. It can be a cubic, a quartic, blah blah blah. You can choose. There's like more things to deal with. But yeah, that's the end of the part one of 2601-2501 revision seminar. Hopefully this was helpful. The part two of the revision seminar is on the 11th of August. I think that's a Thursday at 2 p.m. So same time, where Jay and Bruce will be taking those to like the second part. So yeah, hopefully, yeah, good luck for your exams, and I guess bye for now.